Okay, good afternoon. Welcome to the seventh lecture of EP1027, Maxwell Equations and Electromagnetic Waves. So the agenda for today's lecture is the following. First, I'm going to do a very short review of the last lecture, maybe 2 or 3 slides on electrostatics. We said a lot of things there, so it's better to review, and I think this review will be beneficial for you when you take the quiz later in the afternoon or in the evening. Then I'm going to talk about charges in motion. We will see what happens when we look at the fields produced by a point charge which is moving with uniform velocity little v. And it will turn out that in addition to creating electric field, it will also create a magnetic field. That is, if you bring a magnetic needle or a compass in the vicinity of a moving charge, the magnetic needle or compass will start swinging. So which indicate that the charge in motion creates not only an electric field but also a magnetic field. And then I'm going to talk about steady currents, in which are conductors in which you can think charges are moving with uniform velocity. Steady currents actually means, most of you know, currents which are not varying with time. And in such conductors, we will see that to set up steady currents in conductors, we need a certain condition fulfilled, which is known as Ohm's law, which is fulfilled in a lot of kind of conductors such as plasma or electrolytes or even metals. So we will discuss this and we will see the consequences of this. And then I'm going to talk about magnetostatics, which is the branch of electrodynamics which deals with steady or static magnetic fields. Magnetic fields which do not depend on time. They do depend on space, but they do not depend on time. And these are, as I said, produced by charges in uniform motion, but also they can be shown that they're produced by steady currents. In fact, from this magnetic field of charges in uniform velocity, we will be able to derive, which I'm not going to show, but you can derive something which is known as the Biot-Savart law, which is the static magnetic field produced by a current carrying element, a piece of a conductor, for example, and we will derive certain conditions from that, just like from Coulomb law we derive the divergence and curl for the expression of the electrostatic field. We will see what are the similar expressions for Biot-Savart law, which tells you what are the divergence and curl of the magnetic field is. So one of those will be the Ampere's law. Most of you have studied this in high school, at least the integral version. Today I'm going to tell you about the differential version as well. And then we will do something which is opposite. So far we were concerned with what kind of fields moving or a static electric charge produces. Now we're going to ask the reverse question, that what kind of force does a point charge experience when it's moving through electric and magnetic field produced by other charges or other current sources, right? And most of you know this answer. This answer is given by the Lorentz force law. We will discuss that, and then we will find out the magnetic force both on the point charge and the current element or circuit element. Finally, we are going to relax the assumption that currents are steady. We will consider situations in which currents are not steady. As a result, we will not have static magnetic fields, but we will have time-varying magnetic fields, and this will lead to a phenomena which is known as electromagnetic induction. Electromagnetic induction will end up creating time-varying electric fields as well. So this is the situation which we will discuss here in this section. When we have time-varying electric and magnetic fields, we will see that we need to modify some of the equations. For example, in electrostatic, the curl of V vanishing, and in magnetostatic, the Ampere law. These two will need to be cured in the sense that they only apply for static situations when we have uniform current or static fields. But when you go to time-varying field, these two laws need to be modified. And this was successfully completed by Maxwell using a very ingenious insight of introducing a certain notion of the displacement current. Most of you are familiar with the story from high school books in which you have this capacitor circuit, and you consider a surface which is enveloping the circuit, and Maxwell found out the rate of change of flux through that, electric flux through that, and he arrived at the notion of a displacement current. I'm not going to go through the history of it, but in terms of equations, we will see how easily we can modify the static situation equations to include dynamical or time-varying fields. And this is where we're going to end today. Okay. The references and reading for this lecture would be Griffith's chapters 5 and 7. Chapter 6, I think, is magnetic fields in matter, so which we will discuss in tomorrow's lecture. So we will skip that for now. And chapter 5 and 7, I think chapter 7 is Maxwell's equations, and chapter 5 is magnetostatics. Okay, so then without further ado, we start the lecture. So the first few slides, as I said, would be a review of electrostatics, what we did in on Friday's lecture. So I mentioned in Friday's lecture that electrostatic fields, the static electric fields, are produced by charges, in fact charges at rest, and the electric field strength, which is usually given by some version of Coulomb's law, obeys the following equations. Divergence of E is charge density over epsilon naught, and curl of E vanishes. These were the two expressions, these were the two sort of static electrostatics Maxwell equations. And most of you are familiar with these two laws from high school, where you have learned this in the integral version. That is, when you integrate this equation, the Gauss law equation, over a volume V. So integral of, let's look at the right hand side, integral of charge density over a volume V will give you total charge enclosed in that volume. And volume integral of divergence of some quantity, we can use Gauss theorem, Gauss divergence theorem, to convert it into a flux integral. So this is the electric flux over the surface S, which envelopes this volume, which is enclosing this volume. So we have this equation: flux through some Gaussian surface, closed Gaussian surface, is equal to the total charge enclosed by the surface inside the surface divided by epsilon naught. So I wanted to point out to an important fact about the system of units. I already discussed that this epsilon naught appears as a result of using units in which you have units of charge is not you have separate units of charge. But however, there is another important distinction between various units used in electromagnetism, which is the idea of a rationalized system of units versus a non-rationalized system of units. So if you look at these equations, you'll see that nowhere in these four equations, which are the differential and integral version of Gauss law and curl vanishing, nowhere any factors of 4 pi's appear. There's no 4 pi appearing anywhere. However, if we remember the expression for the force field, electric force or electric field due to a point charge or Coulomb law, there you had 1 over 4 pi epsilon naught. Okay, 1 over 4 pi epsilon naught instead of. So these kind of units in which in the Maxwell's equations you don't have any factors of 4 pi, and instead you have factors of 4 pi in the force laws. For example, Coulomb law or Biot-Savart law, such units are known as rationalized units. So in rationalized units, Maxwell's equations are clean and they don't have any factors of 4 pi. In non-rationalized units, for example, in some set of Gaussian units, you don't have 4 pi's in Coulomb law, but you have 4 pi's appearing in Maxwell's equations, which is, I think, equally bad. So non-rational units are units in which Gauss law and curl vanishing in general Maxwell's equations have factors of 4 pi, whereas Coulomb law and Biot-Savart law, that is force laws, do not have any factors of 4 pi. So these are non-rationalized units. So anywhere you hear this word rationalized or non-rationalized, you should be able to immediately make the connection that, okay, rationalized means no 4 pi in Maxwell's equation, but instead 1 over 4 pi is in Coulomb's law and Biot-Savart law, whereas non-rationalized means there is 4 pi in Maxwell's equations, but no 1 over 4 pi in Coulomb law or Biot-Savart law. Okay, so this is something I wanted to mention because before I forget. Anyway, so let's get back to electrostatics from the short departure into a system of units. So this was the electrostatics Maxwell equations, both differential and integral version. And then we looked at electric fields in matter, and we learned that when you subject matter to electric fields, electric fields cause the neutral molecule to stretch out, in the sense that center of positive charges and center of negative charges separate in the molecule, and the molecules develop a magnetic moment, electric dipole moment. So developing an electric dipole moment is what is called polarization. And this kind of polarization, we also saw that, well, you can think of the dielectric as a chunk of a dipole, or you can think of it in terms of bound charges. That is, you remove the dipoles, but an equivalent amount of volume charge given by minus divergence of the polarization density, and a surface charge on the surface of the dielectric, which is given by this normal component of the polarization vector. And as I said, if you look at Griffiths, it actually motivates how polarization is equivalent to these kind of charges. Okay, so then for matter, for electric fields, I don't know why I've written EM fields. It should be electric field. Please note that this shouldn't be EM field, but this should be electric fields. For electric fields in matter, new version of Gauss law will come into being, because this row will contain row free and row bound. The free charges are the ones which are we are pushing into the dielectric. For example, if we connect it to a power source and the power source drives the current through the dielectric, that current which is externally pushed into the dielectric is called the free current, or the charges which are being pushed in are the free charges. So because we cannot measure the polarization and we cannot directly measure the bound charges, it's better to phrase every equation we have in terms of free charges. And if you write in terms of free charges, the Gauss law, which we had before, which is divergence of E equal to rho over epsilon naught, turn into a different, looks a slightly different. Divergence of D equals rho free, where rho free is the free charge density, and this D is the electric displacement vector, which is defined to be this epsilon E plus P. Okay. So the integral version of this, again, I think something which you have learned in high school, is that if you have a chunk of a dielectric in any volume inside the dielectric, if you imagine a volume inside the dielectric, the flux of the electric displacement vector through a surface S, which is the boundary of that volume, is equal to the total amount of free charge enclosed in that volume. And you solve a bunch of problems using these two equations. Remember, you use the spherical symmetry to solve and find out the electric field produced by a point charge embedded inside a dielectric. We're not going to do that, since most of you are familiar with that. One more thing is that when you have electric fields, again, this shouldn't be EM field, it should be electric fields. Electric fields across an interface of two dielectrics. So if you can remember the diagram figure we had in last lecture, we had a two-dimensional boundary separating dielectrics 1 and 2. Now at the boundary of the two dielectrics, the displacement field vector on either side is not the same. There is a discontinuity. And the discontinuity is, in fact, in the normal component discontinuity can be shown to be equal to the free charge density on the surface of the boundary of the two dielectrics. So we have a boundary between two dielectrics, and on the boundary there is subsurface charge density sigma of F, and the discontinuity in the displacement vector, or the normal component of the displacement vector on both sides of the boundary, is equal to this free charge density. Also, we showed that curl of E vanishing. So this we obtained from this Gauss law, applying to a Gaussian pillbox-like Gaussian surface, a pillbox-like Gaussian surface which is straddling the two surfaces. Straddling both sides of the surface, both sides of the interface. And considering integral version of the curl vanishing equation, that is line integral of E on a closed loop vanishing on a loop which is rectangular across the interface, we also found that the tangential components of the electric field are continuous. That is, from above and below, both sides of the boundary on the two media, the electric fields, the tangential component of the electric field are continuous. Okay. So then we considered, as we said, we remarked that these are too many equations, because there are two equations, but then D is a new unknown because we don't know P, So D and E are in principle both unknown. We have too many unknowns. And one way to reduce or simplify the situation is to consider linear dielectrics, in which we have something which is known as the constitutive relation, that is D is determined in terms of E. Not only is it determined in terms of E, it is a linear function of E. So in that case, we have a simplification, because these two equations become, you can replace this D by epsilon E and you get some equation in terms of divergence of E. In fact, we considered an even simpler case when we had not just linear, but linear isotropic media, in which D and E are parallel. So this epsilon tensor becomes just a number, a scalar, and D and E are parallel to each other. So the D vector and the E vector are exactly parallel to each other. In fact, D is proportional to E by this constant amount. So also let me remark that we are considering a homogeneous media, which is to say that this epsilon, the relative permittivity or the susceptibility, it is not a function of the location in the dielectric. Everywhere in the dielectric this is the same, right? So this is the assumption we are making. It's a linear homogeneous isotropic media. And then we consider the energy which is stored inside electromagnetic fields, and we showed that the energy density per unit, which is the energy per unit volume stored in electric fields. I'm sorry, again I've written, instead of electric I've written EM fields. An electric field is given by half epsilon naught E squared, if this is the electric field in vacuum. On the other hand, if we have an electric field turned on inside a material media, then the energy stored in the per unit volume of the material media is not just stored in the electric field, but also the fact that we are doing work in polarizing the media. So the work done in polarizing the media plus the energy stored in the electric field, the combined expression which gives you the energy density per unit volume in the dielectric is half D dot E. Okay. Of course, when in the case of when the material media becomes vacuum, in the limit when the material media is vacuum, these two expressions are synonymous. And then we considered conductors, which are defined to be class of matter which have infinite amount of free charges, and as a result of which we saw that any electric field inside gets neutralized because the free charges begin to separate, and on the opposite boundaries of the conductor till, and they get attracted to the, for example, positive charges get attracted to in the direction of the applied electric field, and negative charges get attracted in the direction opposite to that. And this arrangement of charges, free charges, on the opposite end of the conductor leads to an induced electric field. And that induced electric field, because it has an infinite number of free charges, the induced electric field keeps growing till it cancels, completely neutralizes the applied electric field. And once it is done, no charges are moved, they remain as they are. Okay, so E is 0 inside. So as I said, the induced electric field completely neutralizes the applied electric field. So the net electric field inside a conductor is given by is 0, E equal to 0. Now if you apply Gauss law inside, divergence of E is rho, but E is 0, so divergence of E is 0, so rho is also 0. So for static electricity or electrostatics, we have the condition E equals rho equals 0 inside the conductor. However, we will see that this will get modified when we are looking at steady currents, and we will not have this condition true. Only half of this will be true. It will not be fully true. And then we also discussed that the electric field is normal at the boundary. So all the charges will clear away from the bulk and reside on the boundary, giving it an induced boundary charge, surface charge density sigma. And the electric field on the boundary is given by, just outside the conductor, is given by sigma over epsilon naught times the normal at the surface normal, n hat, outward surface normal. So this we established this using Gauss law, which is known as Ampere's theorem. This result that at the surface of a conductor, the electric field is normal, and it's proportional to the charge density, surface charge density. And then we also briefly mentioned the concept of a capacitance of a conductor. Like given we saw that the conductor is an equipotential surface, and the amount of charge, entire charge which is on the conductor is proportional to this potential of the conductor. And the constant of proportionality is sometimes known as capacitance. This is a slightly special case when you have one conductor, sometimes we just call a capacitor or a condenser. However, usually when we look at such kind of setups, we have a bunch of conductors. So let me denote them by indices I and J. I runs from 1 to n, let's say. So we have a bunch of conductors which are held at different potentials phi comma j. So the conductor 1 is held at potential phi 1, conductor 2 is held at potential phi 2, conductor 3 is held at potential phi 3, so on and so forth. So, and then you can ask, what is the relation between the ith charge, or charge on the ith conductor, with the potential on the jth conductor? Okay, so it's slightly asymmetric. It's not the same thing as here. We had one conductor, so current on the first conductor equal to C times current on the charge on the first conductor is equal to C times potential of the first conductor. Here we have a slightly different equation. As you can see, this is a linear sum because J is a repeated index, so that it's being summed over all J, right? So this is the sum. So the idea is that ith conductor, charge on the ith conductor is proportional to the jth potential of the jth conductor, and the proportionality constant is known as the coefficient of conductance, Cij. And it will turn out, I will give an exercise in which you have to show that there is something which is known as Green's reciprocity theorem. In fact, it is already there, I think, in the homework assignment. Please check that Cij equals Cji. So this is reciprocal behavior. If you make the potential at the jth conductor and you assign some charges on the ith conductor, the coefficient of proportionality will match when you reverse the situation. Okay, so this is sometimes known as Green's reciprocity theorem. Please check out the assignment where I have given this as a solved example. And then we switch to the potential formulation, in which because curl vanishes, we can write the electric field as a gradient of a scalar. And then the Poisson equation, which is just obtained by plugging in the Gauss law, the fact that E equal to minus gradient of phi. If we put gradient of phi here, we get the Poisson equation. So Poisson equation for vacuum is Laplacian of phi equals minus over epsilon naught in vacuum. And for linear isotropic media, you can show that it is equal to the free charge divided by the absolute permittivity of that medium. Also, the Poisson equation, we generally talk about Poisson equation as the second order elliptic partial differential equation. And you need some boundary conditions to solve this, given a volume of charge and a given region of space. We need to give some data on the boundary of that space so that we are able to solve this equation. And those are these equations, in which first is that the potential is continuous across any boundary, and second is that the Gauss law gives you the normal derivative of the potential times the epsilon of that region is discontinuous, and it is equal to the amount of free charge deposited on the boundary of the two dielectrics. And of course, that the electric field being continuous at the boundary, tangential component of electric field being continuous across the boundary, means that the tangential derivative of potential across on both sides of the boundary should match. These matching conditions are important and to solve this equation. Okay, so this is a two slide summary of what we did in the last lecture, which was a lot, but I think this summary will help you in today's quiz. So now if we are all done with electrostatics, let's move on to magnetostatics. But before that, we want to look at magnetic fields produced by charges in motion. So here, if you look at the title, it says magnetic fields, these are produced by charges in motion, and it affects other charges in motion also. Okay. So what am I talking about? So let's consider charges which are moving at low speeds, let's say low uniform speeds, with a velocity v, and the magnitude of velocity is much less than the speed of light. This is what I mean by low speed. Now we have two reference frames which we will talk about frequently. One is the lab frame, in which we see the particle moving with the velocity v, and it's the rest frame of the charge, in which the charge is not moving but it is static. So it's the reference frame which is attached to the charge which is moving with velocity v. So most of you know from high school that these two frames, there is an equation relating them, which is x prime equal to x minus vt, or vector x in this lab frame. This is unprimed are in the lab frame and prime is in the rest frame. In particular, the origin, which is x prime equal to 0 and t prime equal to t prime, let's say, will be given by the trajectory x prime equal to 0 means x equal to vt, so which is the point particle moving with the uniform velocity. This is exactly what we have here. So these are known as Galilean transformations. You might wonder why I have written approximate signs instead of equality signs. The reason is that these are not the actual transformation law. Galilean transformation laws are approximation to the accurate transformation law. They're only an approximation to the actual transformation law, which is known as Lorentz transformation law. Some of you might have learned it in modern physics course or special relativity class. However, special relativity is not going to be a part of this course, so that's why I've skipped it. Instead, I've gone for the Galilean version of the equation, of the transformation equation from one inertial frame to the other. Also, in the rest frame of the charge, that is in the frame which is stuck to the charge, we don't see any magnetic field because it is electrostatics, because the charge is not moving. Then there is no magnetic field and we only see the Coulomb law. Okay, the electric field is given by the Coulomb law in a frame which is at rest with respect to the charge. However, when we conduct experiments in the lab, it reveals that the electric field, so this is E prime, meaning this is the, anything which is prime should mean in the frame in which the charge is at rest. Okay, and E and everything without primes mean the lab frame, laboratory frame. So in the laboratory, when we look at the electric field and magnetic field produced by this, using various other, just as Coulomb arrived at his law experimentally, we can do experiments to find out what is the measured the electric field produced by this moving charge, and it will turn out that is given by this expression, which is almost like Coulomb law. It is Coulomb law, except instead of x prime you have x here. Okay, instead of x prime you have x here. The denominator remains the same, however the numerator changes to x. Instead of x prime you have x here. So if x prime is the trajectory of the charge, which we know is x minus vt, because we have this equation. Also, if you put a magnetic needle on the vicinity of this moving frame in the lab, the magnetic needle swings, which tells us that it is the moving charge is also producing a magnetic field. And using experiments and doing experiments with compulsion needles, magnetic needles, we can figure out what is the expression for the magnetic field of a moving charge, and it seems to be given by this expression. Okay, Q times proportional to V over C square. So this tells you that if V is 0, this entire expression goes to 0. So if a charge is not moving, then there is no magnetic field. So it's directly proportional to velocity. And then this is the vector cross product. This cross doesn't mean normal multiplication, but this is a vector cross product, okay? Because this is a vector here, this is a vector quantity, and then this is the denominator we had before, okay? These we cannot derive unless, of course, you know special relativity. So from an experimentalist point of view, these two laws you determine just as you determine Coulomb law, which is by experimentation. So this is the first part. This is the kind of magnetic and electric field which are produced by charges in motion. Now you can ask the reverse question. If I introduce a electric charge in an electric and magnetic field region, how are they affected? So the question is, how do magnetic field affect charges? Say a charge big Q moving with a velocity big V in a region with magnetic field big B. So I've written big Q and big V because I want to distinguish between the two charges. One of first charge is moving and producing the magnetic field B. The other guy is actually experiencing some force moving through the field produced by the little v and little q. Okay, so that's why big Q and big V are the test charges, and little q and little v are the charge and velocity of the source which is creating this magnetic field. So the answer is provided, most of you know, is by the Lorentz force law, which tells you that a charge in motion with the velocity v experiences the force which is given by q v cross b. So one thing about the units and dimensions, I guess, of magnetic and electric fields, I would have preferred to use a more democratic system of units in which E and B have the same units or same dimensions. But here we see they clearly do not, because the electric field is Q times E. Force produced by electric field is QE, while this is QV cross B. So dimensionally, electric field is equal to velocity dimensions times the dimension of magnetic field. Please keep that in mind. Okay, so this slide is about what kind of magnetic field is produced by a moving point charge, an electric field produced by a moving point charge, and what kind of force is experienced, by a moving point charge inside a magnetic field. Okay, so now in order to make progress, we will learn a little bit about steady currents in order to get to magnetostatics. Clearly, this is not magnetostatics because magnetic field is a function of time. So let me look at something which is known as steady currents, which is Ohm's law, which will lead to Ohm's law. So steady currents are, as most of you can tell, are in a situation in which the current is not, rate of change of charge with time is not varying. This is very hard to do. Consider any conductor, such as a metal or a plasma which is a gas of ions, or electrolytes, which is the liquid in which ions are moving around. In fact, to a great extent, even a metal can be thought of as, the electrons which are moving around in the metal can be thought of as a gas itself. In either case, these are all fluids in which charges are moving around freely. Now, it so happens that these charge carriers which are moving around actually are not moving in straight lines. They are getting scattered away by other charges. They collide with other charges. For example, inside a metal, you have the lattice sites where the ions are sitting, and the electrons are hit by that or collide with that or get absorbed in those. And similar thing in plasma, similar thing in electrolytes, they are scattered or kicked around by larger ions. So whenever such collisions occur, momentum and energies are lost from the charge carriers to the lattice or to the general mass. This will produce sort of heating. Most of you know, and this is known as Joule heating. Excuse me. It's known as Joule heating. So in order to keep charges or moving at a constant rate, or current at a constant rate, we need to feed energy into the metal or plasma or electrolyte. So to maintain steady current, we keep supplying energy in the form of electrical energy or electrical field. So in order to produce a constant steady current, we need to keep on introducing a constant electric field inside. Okay, so then we have this relation which is true for not too strong fields, and then such kind of a relation is known as Ohm's law. This is something which is known as Ohm's law. Although this is not exactly the version of Ohm's law which you learn in high school, V equals to Ri, it can be shown that you can show that this will indeed be same as Ohm's law, but in a differential version. So J is what is J? J is the current density. What is current density? So most of you who have not read Griffith at this point will not be familiar with this quantity J, but J is the current density. Remember, current density is the amount of charge flowing per unit time per unit cross-sectional area of the flow. So if you have a current going around x direction, then in the amount of charges flowing through the YZ plane, or per unit area of the YZ plane, is the current density. So it's always charges per unit time per unit normal cross-sectional area. Okay, so that is equal to sigma times the electric field, which electric field, as you know, to create an electric field, we need to pump energy. to create electric field. So this constant creation of this constant electric field or maintaining this will cost us energy, and that is used in keeping the charge density constant. So sigma, this constant of proportionality, is known as the electrical conductivity, and it is the inverse of resistivity. Most of you know this. So for steady currents, what, as I said, means that the charge density is not varying with time. It's always constant. Del rho delta equals 0. So then continuity equation, which tells you del rho delta plus divergence of J equal to 0, means if del rho delta is 0 individually, then divergence of J should also be 0. Right? So divergence of J vanishes, but then J is equal to sigma E. So I can plug in sigma E here, and it will give us divergence of E will also vanish inside the conductor. Okay? But divergence of E vanishing is nothing but rho vanishing, because divergence of E is equal to rho over epsilon naught by Gauss law. So divergence, so let's review this argument. Because of steady current, that is time varying, there's no time varying charge density, means divergence of J vanishing, and because J is proportional to E, this means divergence of E vanishing. But divergence of E is equal to the charge density over epsilon naught, which is Gauss law. That means divergence of E vanishing means rho vanishing. So there is no charge inside the conductor. This is pretty much the intuition we had in electrostatics. In electrostatics, we had no charge residing inside the bulk of the conductor. However, although divergence of E vanishes, E itself doesn't vanish, because we want to maintain a constant steady current inside. E cannot vanish. So a big difference from a static situation. This is not a static situation. This is a steady current, so it's a dynamical situation in which current is being pumped in. So rho is 0, but E is non-zero for steady currents. So for static situations, static charges, we had both of these to be 0. But when we go to steady currents, E cannot be 0 anymore. It is not consistent with these equations. In order to have steady currents, you must have a non-vanishing electric field. Otherwise, it won't be steady current. If you remove the electric field from inside, you cannot maintain a steady current. Okay, so now we will see what is the effect of such steady currents, and we will see that it will lead to the production of static magnetic fields. So that's why magnetostatics, and it is given the static magnetic field which will be produced is known by the famous Biot-Savart law, which most of you have read about in high school. And we will also see that the existence of a magnetic vector potential and the Ampere's law. Again, something which you have learned in high school, maybe not the differential version, but definitely the integral version. So Biot-Savart law is the magnetic field produced by a current element, so a conductor element. So inside a conductor you have any given region, any small infinitesimal region, which is the current, and current is passing through that region. So the amount of the current carrying element is given by this current density times the volume and infinitesimal volume element. It's like a double adjective. I'm using both infinitesimal and volume element. Either we use volume element times the current density, or infinitesimal volume times the current density. So this is a current element, and it says that the magnetic field produced by a current element is given by the current element times the R over R cubed, the difference between the location of the field and the location of the source. So that vector, which usually people call as R, I'm calling it x minus x prime, divided by, so it's an inverse square. Again, it's an inverse square law. So it is inverse square law, however, it is not along the line joining the two elements, not line joining the source and the effect, source and the field point. It is not along that. So I forgot to mention something which is very important, which I should have. So if you consider the force experienced by a point charge moving in a magnetic field, and let's say this magnetic field is produced by another charge, little q, moving with the velocity little v, then you can compute plug this expression for v here, magnetic field here, and you can compute the expression. And you can show that the force on this particle due to the first charge is not the same, equal and opposite, of the force experienced by this particle due to motion of the second charge. So right here you can see a violation of Newton's third law. Magnetic force doesn't obey the fact that these are equal and opposite. They are not action and reaction pairs. Okay, it's not a good analogy to think about magnetic field in general, electromagnetic fields, electromagnetic field forces as equal and opposite. Anyway, let's jump ahead. So this you can actually derive from this equation. If you break up the current carrying the circuit into small elements, and each small element you think with elementary charge moving with some velocity v, then using this, integrating over the whole circuit gives you the Biot-Savart law. Again, look in the assignments. I think I have done the derivation there. This is not how things are usually presented in textbooks. This is the beginning point of electromagnetostatics. You start with magnetic fields produced by current elements, steady current elements. However, the way I am approaching the subject is the logical way, not the historical way, in which a person would first detect magnetic fields produced by moving charges, and then conclude from that a current carrying wire or circuit will lead to the production of a magnetic field given by Biot-Savart law. So Biot-Savart law for us is a consequence of the of this formula. Okay, magnetic field produced by point charge. So this is the magnetic field produced by a steady current. As you can see, there is no time anywhere, telling us that this is the static magnetic field, not time varying. It is time independent. Not only that, you can take curl of both sides, and you can see curl, when the curl will hit this guy, it will give us 0. So what you will have here is that divergence of both sides. If you take divergence of both sides, this divergence will get turned into the curl of this quantity, divergence with respect to the x. And you can check again, by now you are more or less experts in vector calculus. You can use the index notation and the Levi-Civita tensor to find out what is the curl divergence of this quantity. Levi-Civita you can use to write down this cross product, and then you'll be able to show that indeed this is divergence of B vanishes. So one thing which I introduced is mu naught, a new constant of nature, so-called constant of nature, which is actually nothing, just the artifact of using horrible units. And this is actually, if you start from this law, this 1 over c square and 1 over epsilon naught will actually give you this quantity. Okay. Actually, there might be a mistake. There must be an epsilon naught here, which I forgot to write about. Okay, so there might be a 4 pi epsilon naught here, which I missed. Yeah, the 4 pi is there, and then the epsilon naught and c square gets combined into this quantity. Okay, so magnetic field produced by a uniform of a charge element or steady current element is divergence free, and most of you know that any vector field which is divergence free implies that the vector can be written as curl of another vector, which is known as the vector potential. Okay, so divergencelessness of B leads to existence of a magnetic vector potential A. Also, we can write down the integral version of this equation, which I guess you're familiar from high school. You apply this to a volume which is bounded by a closed surface S, and you can show that the magnetic, because the right hand side is 0, integral of 0 will still give you 0 over a closed surface, and the left hand side will give you that the flux over a closed surface S, which is enclosing that volume, the magnetic flux through that closed surface is 0. So this statement, and this famous statement that the magnetic flux through a closed surface vanishes, is known by the slogan, "There are no sources or sinks for magnetic field lines." Our magnetic field lines are closed loops. So this means because remember the way we are imagining flux is some kind of lines which are penetrating that surface. But because the flux is zero, the lines which are penetrating must come back, curl around and come back and penetrate the surface inside. Once they go from in to out, they must also come back from out and thread the surface back in. So that means magnetic field lines are closed loops. You can have this for an infinitesimal loop, infinitesimal small closed surface in the limit of a point surface, and which you can show that the magnetic field lines are closed loops. Okay. Unlike electric field lines, which begin on positive charge and terminate on negative charge, there are no such thing. Magnetic fields are closed lines, and they do not need positive or negative magnetic charges to end at or begin from. Okay, so there are no. This is the same thing as saying there are no sources or sinks for magnetic field lines. Okay. And then we have the curl of this expression, which you can take curl of both sides. Again, please you already know vector calculus. Please do these calculations, the elementary calculations yourself. If you take curl of both sides, you should be able to show that if you curl will hit this guy and turn it into a divergence, which will give you the Dirac delta, which will give you integral of Dirac delta will just convert this x prime into x. So you have this equation, which is known as Ampere's law. Perhaps you're familiar with this in a more familiar version when you integrate this over open surface. If you integrate this over an open surface, then the flux of current density through the open surface is giving the total amount of current crossing that open surface. So surface integral over an open surface, or the flux of J, will give you I, mu naught I, and then dot n dot ds surface integral will give you, according to Stokes' theorem, b dot dl along the boundary of the curve, boundary of the loop, which is the boundary of the closed surface, which is the loop C. So it tells you that the circulation of the magnetic field, or the line integral of the magnetic field along a closed loop, is equal to mu naught times the current threading through that loop. Okay, current which is passing through that loop. So we have seen that out of the two equations for the magnetic field, divergence B is 0 and curl B equal to mu naught J. Divergence B equal to 0 implies the existence of vector potential. And now you can ask, if I plug this in this Ampere's law, what kind of equation I get for the magnetic potential? And it turns out that the equation you get when you insert B equal to curl of A in this equation, equation 2, what you get is a Poisson-like equation for three components of A. So if you forget about the second term, so curl of A will give you these two terms. If you forget momentarily about this term, you get Laplacian acting on A equals minus mu naught J, which is almost like Poisson equation, right? Almost like Poisson equation, had it not been for this term. In fact, after a while, we will see that this term can be indeed eliminated, and it will immediately become like Poisson equation to a great extent. Now the Lorentz force law. So this is a summary on one slide summary of magnetostatics. The essential elements are Biot-Savart law, and then the divergence of that expression for Biot-Savart law and the curl of that. Divergence of that will lead to the vanishing of that, and which will lead to the vector potential. And of course, curl will lead to the Ampere's law. Magnetic forces are conservative forces. Most of you know the Lorentz force law, which you've encountered in high school. That is the force acting on charge q moving with the velocity v in a magnetic field region, in a region with magnetic field B. This force is conservative because no work is done on the charge. So F dot dx, force and the displacement of the charge, but the displacement of the charge can be written as v dt. This is v dt, but then F dot v is 0 because the F is proportional, is cross product of v and b. So dotted with v, it will give you 0. So magnetic fields do no work. This is another slogan. which is that magnetic fields do no work on the electric charges, and this produces very interesting kind of trajectories. So in Griffith's, I think in chapter 7 or maybe some later chapter, many such orbits are worked out. For example, you have a region containing constant electric and magnetic fields, and it's interesting to see what kind of trajectories charges take under these. For example, they can be crossed E and B, that is, E and B are orthogonal to each other, or sometimes E and B are parallel to each other, in which they will create helices. The charge will move like a helix. Most of you, I think, have done this in the last year of high school, but it's nice to work out the actual equations. So Griffiths also has, for example, for crossed E and B, you get something which is known as a cycloid. These are important when people are working in, for example, the branch of accelerator physics, in which they're observing elementary particles, their motion in electric and magnetic fields, and they want to control their motions. Then they do that by subjecting them to E and B in a way they desire, in a manner they desire. Now, force on a point charge can lead to the expression for a force on a current element. All we have to do is so this is dq, so instead of q I have a little elementary charge dq, and dq times v is dx dt, v is dx dt, and then this dt I can transfer to q, and dq dt most of you know is current. So the force on a charge element leads to the expression for a force on a current element, which is I, the current, times dx, which is the direction of the current element, crossed with b, right? This is also something you have learned in high school, I think. Now, analyzing, so if you introduce a circuit inside a magnetic field, the force on the whole circuit will be given by integral of this force, right? Most of you know that in some cases it will also produce torques and whatnot. Well, it doesn't do any work because magnetic forces do no work. Now it so happens that if you start fluctuating this B, then a strange phenomena happens. Then actually these statements are not true. Then the magnetic fields will do some work because they will create an induced electric field, something which is known as electromagnetic induction. So what happens is that you have a conductor, just like here you had a charge current carrying element, like a piece of a conductor inserted inside a magnetic field. Now you fluctuate this magnetic field. Now when you do that, the flux through the circuit changes, and Faraday, using some great experiments, showed that this leads to the creation of an electric field through the circuit. In particular, let's say even I is 0, so initially there was no current, and you have an empty circuit without charges. And if you change the magnetic field in which it is placed in this current free, it leads to the production of current. So, and current is only produced by electric field. So that led Faraday to his famous law of electromagnetic induction, which says that the electric field induced on a conductor, which is placed inside a fluctuating magnetic field, is given by this line integral of the electric field, which is just the potential, to be honest, is equal to electromotive force, or electromotive force is the voltage which is created in that circuit, is equal to minus the magnetic flux through that circuit. Okay, so E dot dl equals d phi b dt, or phi b is this quantity. So d dt of this integral, d phi b dt is d dt of this integral. But if you ddt, you can take it inside, and as I said, whenever you take a ddt inside, what you ought to do is to convert it into so whenever you take a total time derivative inside a spatial integral, you have to convert that into a partial derivative, right? So this will be del b del t, and curl of E dl on a closed circuit, such as the conductors, closed circuit inside a closed circuit, you can use Stokes' theorem to convert this loop integral, line integral in a loop, to a curl of E on the surface, which is which is bounded by this loop. Okay, so then you'll get a surface integral on this side and a surface integral on this side. On this side, and you can show that these two equations imply that curl of E plus del B del T equal to 0. In other words, curl of E equals not minus del B del T, so curl of E is not vanishing. So when you have fluctuating or time varying magnetic fields, curl of E equal to 0 that equation doesn't hold, and instead you have electromagnetic induction, which will create curl of E equal to minus del B del T. So if B is constant with time, you get back electrostatics, the electrostatics law, curl of E equal to 0. However, B is fluctuating with time, curl of E equal to minus of del B del T, which is not 0 now. So does this produce some kind of inconsistency? And the answer is no. The reason is, if we look at the other law, which is known as Ampere's law. Now remember, Ampere's law is curl of B equal to mu naught J. Now a curious thing happens when you take divergence of both sides. Divergence of J and divergence of curl of B. Divergence of curl vanishes. So what you get is divergence of J equal to 0. Continuity equation tells you divergence of J equal to minus del rho del T. So del rho divergence of J is not 0 in general. It is only 0 when rho is constant, is not a function of time. But in general, this is also not 0. When you have time varying situation, when charges are fluctuating with time, divergence of J is not 0. So Ampere's law doesn't really apply to the generic situation when you have time varying fields, charge distributions as well. So Ampere's law needs to be fixed as well. And this was done by Maxwell in a great, in an ingenious trick. He was able to figure out what to do, how to modify Ampere's law, which is curl of B equals mu naught J. He said curl of B is not equal to mu naught J, but you have to add another term, which has dimensions of current and has so in vacuum, epsilon naught E is just the displacement field. So this is like del D del T. Epsilon E times del E del T is, if you take this epsilon inside, epsilon E is D. So this is del D del T. So this term he called displacement current, because this is rate of change of the electric field displacement, and it has the same dimensions as current. And he said, if you, instead of mu naught J, if you introduce the second term, then everything is consistent. In fact, let's check if it's really true. So if I take divergence of both sides, divergence of curl vanishes, so this is 0. And divergence of this side will give you divergence of J. And then divergence will hit this guy. Divergence of E is equal to rho by epsilon naught. So this is del rho del T, and the epsilon naught cancels. So indeed you get divergence of J plus del rho del T, right? So this is continuity equation. So this side is also 0. So both sides are 0 in arbitrary situations. So this is the new and improved version of Ampere's law, which should be called Maxwell's law, because Maxwell is the one who fixed it. And this relation is sometimes known as the Faraday-Lenz's law. So now we have the correct Maxwell equation, which applies for all situations, not just static situations, even dynamical, or in which you have fluctuating electric and magnetic field, fluctuating charge distributions. So the first law is Gauss' law. Most of you know this from electrostatics. This has been with us, and this doesn't undergo any change. However, the curl vanishing law does undergo a change, which is known as Faraday law, because it was figured out by Faraday that curl of E plus del B del T equals 0. And then the third equation, which is magnetic field, has no divergence. It has no sources of sinks. Our magnetic field lines are closed loops. So this also goes unmodified in the full theory. And finally, you have Maxwell's version of Ampere law. So this should be called Ampere-Maxwell and not just Ampere. Mu naught epsilon naught, this quantity I've written as 1 over c squared, most of you know, so that's why you have 1 over c squared instead of mu naught epsilon naught. So one thing I want to draw to your attention to is the total number of equations on this block. So this is the scalar equation. It has only one component. This is the scalar equation, one component. This is a vector equation, so it has 3 components, and this is 3 components. So 3 plus 3, 6, and 2, 8. It seems like there are 8 equations, but the number of components of electric and magnetic field combined is 3 plus 3 is 6. So how is it that for six entities or 6 components whole, we have 8 equations? What is going on? Why do we have this mismatch? For 6 unknowns, we should have 6 equations and not 8 equations. So what is going on? And you should try to figure out. If you cannot figure out, I will tell the answer in the next class. But you should think what is going on here. Why do we have 8 equations or 8 equations for 6 variables? Okay. So a closely related thing is to look at the first and the fourth Maxwell equation. One is the scalar equation and the other is the vector equation, of course. But the important thing to look at the right-hand side of both equations. The right-hand side of both equations contain the sources. For example, electric field is produced by charge density. The charge density is sitting here. And magnetic field is produced by steady currents. The current density is situated here. So, these first and the fourth one, which is Gauss law and Ampere Maxwell law, they're truly equations of motion. As the RHS, the right-hand side contains the sources. They tell you how or what kind of field is produced given a source. So given a source, which is rho and j, it tells you what E and B should be using this equation. In contrast, the other two equations, that is the middle two equations, Faraday law and no source or Sinks law, have no sources. Right hand side is 0. So they must hold for all situations regardless of whether source or what kind of sources are there. It could be a wire, it could be a cylindrical source, it could be volume distribution, but these two equations must always hold. So it's not prudent to think of these equations as equations of motion. Rather, you should think of these as constraints that must hold in all situations, all solutions of electric and magnetic field. Any kind of source which produces any kind of field must satisfy these two equations. So these are constraints which have to be satisfied by any electric and magnetic field. Otherwise, they don't. If you find some solution of these two equations which do not obey these two equations, they are not good electric and magnetic field. They are not bona fides. So we have to reject them. Okay. So these two equations, these are called homogeneous Maxwell's equation because the right hand side is 0, and these two are sometimes the first and fourth one are called the non-homogeneous Maxwell's equation, plainly because the left hand side, right hand side is not 0. So the homogeneous Maxwell's equation is sometimes known as Bianchi identities. They're not equations of motion, they are actually consistency conditions which shall be satisfied by all magnetic, electric and magnetic fields. Now, as I said, that we always try to switch to potential formulation because many times they lead to reduction of the number of degrees of freedom from vector to scalar, for example, and they simplify situation. And most of the work, historical work, has been done in terms of potential. So, but I think we lose the scalar potential because curl of E is not 0 anymore. So curl of E is minus del V del T. This is what was elucidated by Faraday. So curl of E is non-zero, so that seems like we cannot define an electrostatic scalar potential anymore. So all hope is lost, is it? Let's see if that is true. Well, one thing is true, that magnetic potential is still there because divergence B still vanishes even in time-dependent situations. So we still got the vector potential, although it's not. We are not so enthusiastic about it because it doesn't really lead to a reduction of degrees of freedom. B had 3 components, A also has 3 components. So it's a vector quantity from vector quantity. So it doesn't really excite us much, right? So okay, good. Okay, this is okay, but not a big deal. Now things take a turn for the good when we substitute this in the Faraday law. Okay, so this is the Faraday law, curl of E equal to minus del V del T. Now instead of B, we substitute curl of A here, and then we switch the curl with the del T. So curl will go outside and del T, because these are spatial and time derivatives, they commute with each other. And we have this new equation, Faraday's law. If you bring on this side and write B equal to curl of A, you get curl of E plus del T equal to 0. So now this is beginning to look like something which we recognize. Curl of some vector quantity is 0, and curl of some vector quantity 0 means that vector quantity, in this case this is this, must be equal to gradient of a scalar. Or in other words, E is equal to minus gradient of phi minus del A del T. Right? So we can still define a new scalar potential, except it doesn't determine the electric field directly. You need both the scalar potential and the magnetic vector potential to determine the electric field. Nonetheless, you still have less number of components. Now you have A and phi altogether three components and 1 4. And previously you had E and B, which was 6 components. That still leads to a reduction in the number of components. So we will still value that we can do this thing. So these are the two. In the case of time varying situation, when you have time fluctuating fields, then B is curl A and E is not equal to minus gradient of phi, but minus gradient of phi minus del A del T. So these are the general case, okay? So we see that the we can invent an electric potential for time varying situation, except it doesn't determine the electric field by itself. It also needs the vector potential to define the electric field. And you can ask, what do Maxwell equations look like if we substitute in terms of A and phi? What do Maxwell equations look like? We know for electrostatic, for example, the Gauss law looks like Poisson equation, right? We might ask, what do equations? So this led to the existence of the electric potential, new electric potential. This led to the equation of B establishment, the fact that B is equal to curl of A. So these equation has been taken care of already in some sense. Now we want to plug in E equal to this in the first equation and in the fourth equation, right? So if we do that, simple vector calculus will tell you that you get two equations. The first equation, it is not anymore the Poisson equation. So the bits and pieces of Poisson equation you can recognize. The first term on the LHS and the RHS are Poisson-like, but the second term is non-Poisson-like. You have an extra term. Del T of gradient of divergence of A is there. If nothing is fluctuating with time, del T will go to 0 and you get back your Poisson equation for electrostatics. Ampere's law looks something a bit more ghastly. It's a vector equation, so each term is a vector. So the right hand side is obvious, it's a vector because mu naught is a scalar multiplied with a vector, and this guy is a scalar operator acting on a vector, so it's a vector, and this is a vector operator acting on a scalar quantity. So indeed both sides are vector, but they still look very nasty. It is not as pleasing to look at as it was when you had just Poisson equation, right? So this is still a nasty looking equation. However, this is not the last word. You might think this is nasty and there is no point. Potential doesn't seem to simplify life. Potential formulation doesn't seem to simplify life. But hold your thoughts for a second, because there is a miraculous property of the vector and scalar potential which is going to emerge from these equations. What you can show, because remember we discussed that A is ambiguous up to addition of a gradient of a scalar, because curl of both sides is the same. So both A prime and A are good enough candidates to be a vector potential for B. Vector potential is non-unique, and the non-uniqueness is given by a gradient of a scalar. As it turned out, the new electric potential is also ambiguous, and in fact this ambiguous up to addition by the same time derivative minus the time derivative of the same scalar. And you can again check this, just like we saw that A and A prime gave you the same B. You can show that phi prime and A prime, this given by these two blue equations, give you the same equation for E. So if you insert the blue right hand side here and the right hand side here, everything cancels out and you get back your original electric field. So these two have become ambiguous, and there are many pairs of electric and vector potential which give you the same pair of E and B. Okay, not just A phi. For every A phi there is A prime and phi prime and so on with an arbitrary, and chi is an arbitrary. Remember, chi is a completely arbitrary scalar. There is no restriction on chi. So there is an infinite amount of ambiguity in the vector and scalar potential now. You might think this is a bad thing and everything looks hopeless. This equation looks nasty. The electric and magnetic vector potentials are out of control. They are completely arbitrary, seems like. But hold your breath for a second. Things are going to improve. So this symmetry, this fact that we have an ambiguity is going to be very good for us. That the magnetic vector potential and the electric vector potential can be changed in this way without changing the physical consequences. The electric and magnetic field produced by them would be the same. This ambiguity of definition is sometimes known as gauge freedom or gauge symmetry. I won't explain the origin of this nomenclature, why it's called gauge symmetry or gauge freedom. It is a bit advanced for this class. People who are taking classical field theory at some point will know this why. Using this freedom, you can simplify the Maxwell equation. This is the bottom line. So use this gauge freedom, gauge symmetry, to simplify. Choose a chi so that the following condition holds. Now, compute. Let's say you start with some arbitrary a, and you do this gauge change of variables to a prime. Now you compute the divergence of a, and you keep doing till you get divergence of a plus del phi del t equal to 0. Whatever is the new scalar and magnetic potential, vector potential, you make sure you change in such a way that this quantity is 0, right? Divergence of a plus 1 over c squared del phi del t equals 0. If that is the case, then Maxwell's equation simplify. For example, this will be 0, the second term will be 0, this term will be 0. So we are choosing, because we have a gauge freedom, we can use this freedom to set the condition that our potential is such that we will keep on doing, such that we arrive finally at a vector and scalar potential which will satisfy this condition. And once it satisfies this condition, this equation satisfies. This equation simplifies, because the second term goes to 0. And this second term in the Gauss law or Poisson-like equation will actually become also something simple. And these two equations look identical equations now. So there is Laplacian square minus second derivative of time, 1 over speed of light squared, acting on phi, minus rho by epsilon naught, equals, instead of, this is acting on phi and giving you rho, instead it's acting on a and gives you j. So this operator, this scalar operator is denoted by a box, which is Laplacian minus del t square. 1 over c squared, of course, there. This is called the D'Alembertian operator or the wave operator, because the wave equation is given by this quantity acting on the wave variable, wave field parameter equals 0. Instead, you have a wave equation with the source. On the right hand side, there is a source, which is fueling this wave. Okay, this will lead to electromagnetic wave solutions of the equations of motion of Maxwell's equations. So this is very important. Last slide, as I said, is that if you use the gauge freedom, you can simplify Maxwell's equations to inhomogeneous wave equations. Okay, the last one is the vector equation. So that means for every component there will be a wave inhomogeneous wave equation for ax, ay, az, and which will have right hand side mu naught jx, mu naught jy, and mu naught jz respectively. So here you have 3 such equations actually. Okay. So this is, I will say, is the final form of the Maxwell equation in a very special set of potentials which satisfy this condition, which is known as Lorentz gauge. Remember this Lorentz without the T, not the Lorentz force law. That guy was a different Lorentz, and this is a different Lorentz. Both of them are Dutch, and both of them made valuable contributions to classical physics in general. So let's summarize what we did today. So the summary slide. We am talking about the Maxwell equation field with the potential. The potential formulation is surprisingly symmetric. It's pleasingly symmetric. What do I mean by that? For every scalar, there is a scalar vector, there is a vector source. For a vector source, there is a vector effect. Now, for a scalar source, there is a scalar effect. Okay. Number of sources, which is rho and j, is the same as the number of degrees of potential. Right. Before that, we had E and B. E and B were produced by rho and j. Rho and j had 4 components. E and B had 6 components. So there was a mismatch. However, the potential formulation avoids that, and it nicely tells you the mismatch is gone. So, and then we have this question: why are there 8 Maxwell equations in terms of E and B, while there are just 4 in Maxwell equation when expressed in terms of potential and vector potential? And the answer is, well, they are the same, but as I said, let me go back to, these 2 Maxwell equations are already sort of taken into account the moment we introduce the potentials. The potentials were introduced basically because of these equations. So these two equations are there by just because potentials have been brought in. Otherwise, we couldn't have brought in the potentials into the picture at all. Okay, so that's why these two equations are the ones which are obeyed by which lead to the Maxwell equation in terms of potentials, and there are 4 of them instead of 8 because the other 4 has already been taken into account in the definition of the potentials. Okay. So when one introduces the potential, one is already solving the homogeneous or sourceless Maxwell's equations, and thus getting rid of 4 equations, the second and the third. That's what I mean. All that remains are the inhomogeneous, that is, with sources Maxwell's equations, which are 4 in number. That's why you have just 4 Maxwell equations when written in terms of potentials. Okay, so we will stop here, and next class we will catch up on a little bit on magnetic fields in matter or paramagnetics. We'll have a few things to learn there, and then we will start talking about electromagnetic waves. We are very close because these equations are already starting to look like wave equations. So, okay, I'll stop here. Thank you. So please go through this. Hopefully you'll go through this material, and especially the 2-slide review of the electrostatics which I did at the beginning of the class, because I think that will be very helpful for you when you're taking the quiz. A short review will be good before you start the quiz. Thank you. So we'll catch up on Wednesday.